And now we're going to introduce the concept of having a common ion in solution. So the solubility general rule is that the solubility of a solid becomes low when the solution already contains an ion common to that solid. So we're going to look at an example. Um, so here, calculate the solubility of solid calcium fluoride given the KSP in a zero point zero 0.02 molar solution of sodium fluoride. Okay, so now your solution's composed of, we draw like a little picture. Your solution already has Na or sodium ions and fluoride ions. So you're adding calcium fluoride here, so your common ion is going to be that fluoride. So we're going to kind of see how that comes into play now in our little ice charts. Okay. Before any of the calcium fluoride dissolves, your solution is going to have initial concentrations of sodium, fluoride, and water. Your equilibrium reaction for that salt or equation is going to be broken up into calcium plus 2 aqueous and 2 F minus aqueous. Your KSP expression now, in brackets, you have those two ions raised to the power of their coefficients, and they did give you that KSP value in the problem. Okay. So if you think about an ice chart, or if you just think initial concentration, and then when we reach equilibrium, calcium, there's no moles of, or there's no ions of calcium in the solution to begin with. Fluoride, on the other hand, since you dissolve some sodium fluoride in there, has an initial concentration. So calcium is going to be 0 plus X, giving you just X at equilibrium. Um, and then fluoride is going to be your 0.025, which is that initial concentration of sodium fluoride, plus 2X because of that coefficient. You're producing 2 moles of it. So substituting that in there, you're going to have X, which was the calcium, and then 0.025 plus 2X, and then remember to square it. So just like we did in the last chapter with acids and bases, we're going to kind of take that 2X and assume that it's small or negligible compared to the initial concentration, especially because they gave you the KSP. The KSP is small, meaning that salt's not really going to dissolve that much. So we're going to make an estimate. So we're going to kind of assume that it's small, meaning that we're going to change 0.025 minus or plus 2x to just 0.025 squared, just to make our math easier. And we get x to be about 6.4 times 10 to the negative 8, which is a pretty small number. It's also valid by your 5% rule. So remember that 5% rule being your x over your initial concentration, which in this case, we're talking about F minus times 100. So it would be like taking 6.4 times 10 to the negative 8 dividing by 0.025. It should be under that 5%. So your solubility, or your X value, is equal to that 6.4 times 10 to the negative 8 moles per liter. If you did this without that common ion, you would get a greater solubility because you don't have that ion in solution affecting the equilibrium. If we think about F minus as your common ion, remember that if we go back to acids and bases, this comes from the weak acid HF. This is a weak acid. Therefore, this is a strong conjugate base. Anytime they talk about the pH and solubility, remember increasing pH is making something more basic or adding OH minus. And then decreasing pH would be making something more acidic or adding H plus. So how it will affect your solubility, so say we decrease pH, we have H plus being added to this equilibrium or affecting that equilibrium. That's going to react with F minus. This is a strong conjugate base. Bases want to accept protons. If you introduce a proton to it, your F minus will react with it and form some HF in solution. Um, if you think about that, you had calcium fluoride and Ca plus 2, 2F minus. So remember Le Chatelier's principle. If this is reacting with something, your concentration's going down, your equilibrium then has to shift to the right. If you're shifting to the right, you're producing more ions in solution. This salt is now dissociating or dissolving. Okay. And then the opposite's going to happen for increasing pH. Um, and you're going to force that equilibrium back to the left. So that's what this down here kind of talks about, the anion being an effective base. AgCl is going to be a slight exception because Cl is a weak base. So if we think about the acid it comes from, this is a strong acid. Therefore, Cl minus is a weak conjugate base. So maybe it doesn't really affect that equilibrium. So you're not really going to have any HCl molecules forming. Same thing if you're adding H plus, it's not really reacting with that Cl minus. All right, so I'm going to have you guys submit an answer on here for this critical thinking question. You and a friend are studying for a chemistry exam since you have a lot of time on your hands right now. What if your friend tells you that since acids are very reactive, all salts are more soluble in aqueous solutions of acids than in water? How would you explain to your friend that this is not true? Use a specific example to defend your answer. So since I'm going to try and get you guys to work with a partner, um, for this, I want you to kind of phone a friend here. If you have, someone in the class, someone in the other AP section is fine. Either text them, FaceTime them, communicate with someone somehow, discuss this answer and kind of write your discussion in the answer box on Edpuzzle. So tell me who you spoke with, tell me what you spoke about and what you came up with as a conclusion or an answer to this question.